Thank you. So yes, today I'll present our work on a new relational abstraction domain, which is based on an extension of the union find data structure. And this is work that was done with my PhD supervisor, Matthieu Lemerre, along with another PhD student from my lab, Hichem, Ait-El-Hara, and his supervisor, François, Bobot. And so to show you a small example of how our new domain works, essentially we can run through a very simple input program here, where we build, we have a very small loop that we've initialized with two values 0 and 4, and as we step through the loop, we can learn relations between our variables. So here we'll learn that x1 is x plus 1 and y1 is y plus 1, and we can represent them in this term graph where our nodes are variables and our arrows are annotated by the relation between these variables. Now, as we get to the part where the loop repeats and we go back to the head of the loop, obviously we don't know the exact values of variables anymore, but the relations remain. And what's more, if we look at the two first iterations of the loop, we can actually deduce a relation between x and y because we know their constant values, and that relation is also preserved when we continue stepping through the loop. What that means is that when we exit the loop here, we have lost the exact numerical values of the variables, but we still have the relations between them. And now, of course, we can have an implicit assignment at the call side, but it's just equality, so we can also store that in our graph. Finally, we have another very simple assignment, and here we can prove the assertion because while this relation isn't stored directly in our graph, it's implied by our graph, and we can actually, one of the great strengths of the domain I'm going to show here is that it's very fast, and you can recover that kind of relation extremely quickly. So to give some more general context, in the general field of program verification, your abstractions, they generally fall on a spectrum where the more precise you want to be, the slower you are going to be. On the extremes of the spectrum, on one hand, you have non-relational abstractions, which are very fast, but they only store information, numeric information for each variable independently. And on the other hand, you have the polyhedra domain, which stores linear relations like these between an arbitrary number of variables. And in the middle, you have weaker domains, which are also relational, but generally store a less generic class of relations. So you could have equality instead of inequality, or you could limit yourself to only two variables. And you have the well-known octagon domain where you limit, not only do you limit yourself to two variables, but you also limit the coefficients to plus or minus 1. And where do we fit on this graph? Well, we're all the way over there. The idea is that we are faster than all of these domains, but we are even more restrictive on the relations we allow. So the general form is y equals f of x, where f is going to be some injective function. And for a nice practical example, we have the relation of y equals ax plus b. So to start, I'd like to give some intuition as to how we manage to be faster than all these other domains. And the idea is that the key performance cost in most of these domains is going to be transitive closure computation. So you have this generic theorem in abstract interpretation that when you have information, it's best to propagate that information as much as possible before doing any step for the program. And that can be very costly because, as you can see here, if I want to propagate the information I have between my variables to deduce a relation between x and t, I have two possible paths. I can either go through y or z or just through z. Do I need to explore all my possible paths? And exploring all paths through a graph, well, that's a Floyd-Warshall algorithm, that's cubic complexity. It's fairly expensive. And that leads us to the key assumption of our paper, which is, what if we didn't have to compute such an expensive transitive closure? And so we're going to assume that the relation is going to be the same on any path. And that way, well, first of all, we can shrink our graph. We can only maintain a spanning tree, because thanks to the assumption, we know we're not forgetting anything. And we also know that we can recompute the value between two arbitrary variables very fast, because we just need to look up a single path. Now, there are some quick consequences of that assumption, because it is a very strong assumption. One is that just by reasoning a bit about the shapes of our graph, you'll notice that the composition of relations along our graph edges are going to be associative. They're going to have neutral elements whenever there's a loop, and partial loop paths are going to act as mutual inverses. And therefore, a very natural follow-up assumption is that these relations have a group structure. And this is what we're going to assume because it simplifies the rest of the presentation. But now I can finally present the labeled union find data structure. So as I mentioned, it's an extension of union find. And the idea is we just add these labels, these relations, to the edges of our union find. And the key operation we have is the find, which is that for any connected component in our graph, we can return one distinguished element. And we're just going to modify the find to also add, to return not only the distinguished element, but the relation we have with that distinguished element. So if you call it on an element that has no parent, like R, you return R via the identity relation. And if you call it via to any other element, well, you just follow the arrows to the parent, composing relations as you go, and return that. And one key feature for performance in union find and in labeled union find is that whenever you do more than one composition, you can perform this path compression, which you change the pointer from Y to point directly to the representative. That way you flatten your structure, and any subsequent calls to find will be much faster. But of course, find is kind of an internal technical operations. From the abstract domain point of view, what we care is finding queries like if I have two variables, do I have a relation between them, and adding new relations as I go, of course. So get relation is actually very simple. It's implemented using find. You just call find on each of the variables in your query, and you look if they have the same representative. Then you want to create a variable between them. And here, to get from Z to X, well, you go from Z to R, and then the inverse of from X to R. And of course, if you have a separate cluster with a different representative U, and you want to find the relation between did and U, you call find on both of them. You realize they don't have the same representative, and so you know there is no relation. Now, when it comes to adding a new relation, well, it actually proceeds in exactly the same way as you would in normal union find. You find the representatives of both elements. So this is what the union operation would be in union find. We've called it add relation because it's a little more complex than just a union, but the idea is just the same. You go to the representative and you add an arrow between the representatives. And the idea is as to what label you need to put the arrow. Well, what's the path you do know from R to U? You know you can get from R to Y, you know you can get from Y to V, and you know you can get from V to U. So you just compose all three of these. So yeah, that sums up the data structure. It's a rooted forest with group operations on the labels, and you have these three functions to manipulate your data structure. And one very important fact of these domains is that all three of these functions have amortized constant complexity, so it's a really fast domain. And now I'm going to talk a bit more about using labeled union find in program analysis. So we want to use it to represent relations, abstract relations between variables. And well, a natural question that comes up is what kind of relations are suited? Because when you look at the requirements we have, well, we want to represent relations. So our union find labels must concretize to actual mathematical relations between variables, but they must also be a group. And what we found is that the combination of these two requirements essentially means our relations have to be injective functions. So for example, you can't use interval difference, which I've shown in the previous slides, because that's not injective, but you can use constant difference, which is y equals x plus b. You can also use two-variable linear inequality, y equals a x plus b, as long as you have a not 0, obviously, and your coefficients have to be either rational or 0, because you need to be able to invert the relation. You can have modular multiplication, because on bit vectors, if you multiply by an odd number, you can actually invert that. And for a more bitwise operation, you can also do things like this XOR and rotate relation. Obviously, both XOR and rotation are injective functions, so their composition is as well. And actually, our requirement is a bit weaker than what I've just said. It's not injective functions between the variable values, but it's injective functions between equivalence classes of the variables values, which allows us to have things like this parity comparison relation, which just says if the variables have the same parity or not. Obviously, that's not injective on the whole space of possible integers values, but it is possible on integers quotiented by modulo 2. And another nice fact about labeled union find is that it can combine easily with other domains to help factorize them. So essentially, suppose you have a term graph like this, and you want to store numeric information about all your terms. That can get quite redundant, because if you know the value of y, then you can deduce the value of y plus 7. You don't actually have to store it. So with labeled union find, the idea is very simple. You just store one value at the representative, and then for elements of the class, you can deduce the value. So say if you want to find out the value of y plus 7, you call find on y plus 7, you find its representative, you find the relation it has to this representative, and you look, well, 0,4 is the value at the representative. I update it via my relation plus 7, and I get the value of y plus 7. Set value works very similarly. This time, suppose I learn that 2y is in the interval minus 4, 4. I find the representative, and I shift my interval. This time, there's the inverse of the relation, because I'm taking the edge in the opposite direction. And then I can intersect it with the previous representative's value. And then, of course, I can propagate to subterms and superterms. And already we can see a little improvement of using this domain is because we've factorized our graph, we've essentially reduced the number of nodes. This propagation step will be faster. And so formally, this is done via a function A, which takes a relation, a value, and returns the updated value. And what we found is that this A function must be compatible with the group operations on relations. Essentially, if I want to shift a value via the identity relation, then I must return the same value unchanged. And if I shift a value multiple times via a succession of relations, it's the same thing as if I shifted the value once via the composition of these relations. So A must be a group action. And that actually implies some interesting facts, essentially that the relations we use, the abstract relation we use in our graph, and the abstract values we have on our nodes must be compatible. So for example, if I want to use a constant offset relation with intervals, then I do have an exact action because addition on intervals is exact. If I want to use the TVPE relation with intervals, it is exact as long as I'm working with reals or rationals, because if I'm working with integers and I say I multiply by 2, then I've increased the size of my interval and therefore I've lost precision. For an example where that doesn't work, if I want to use constant offset or TVPE with a bitwise abstraction, so an abstraction which stores for any number, either it's 0, 1, or each bit of a number is either 0, 1, or unknown, well, you can notice that just by adding 3 to this very simple abstraction of 0 or 1, I get 8 possible values at the end. So I've lost precision, and using such a bitwise abstraction with constant offset will lead to precision loss. But of course, that bitwise abstraction works very well with the XOR rotate abstraction, because these XOR and rotate are both operations that can be precisely encoded if you have the bitwise representation of some number. But on the flip side, the XOR rotate relation does not work with intervals. And so this factorizing of other domains, so I've presented it for non-relational domains, but you can also do it for other relational abstractions. So for example, if you have an octagon domain, which tells you facts like z plus x is smaller than some constant, and you also know that y equals x plus b, well, you can just shift that relation along that and learn a similar octagon relation between x, z, and x, and y. And that is actually very interesting because a lot of these weakly relational domains, they have supralinear costs in the number of variables they store. And so being able to factorize this and store fewer relations, because you only store relations with one element of the class and then you shift them to deduct them from the others, you've shrunk the size of your variable space, and so you can gain some very nice precision gains. For another more complex examples, you can use that to eagerly discover all identities in your union finite graph. This one's more involved. You need to store a map at the representative, which is sort of an inverse map of the union find, and therefore it comes with an extra overhead, but it's still very cheap, and that way you can easily discover all equalities no matter which order you put them in. And one last point I want to touch on here is what happens, well, a limitation of union find you might notice is that in abstract interpretation, we like our states to be immutable because whenever we hit control flow split, we want to be able to copy the state to study each branch independently and then join their different values at control flow join. And of course, union find is a very mutable heavy structure. It relies on pointers, it relies on mutating data, and copying the whole thing could be quite expensive. And so one solution we found, which works a lot better than you might think, is only store in flow insensitive relations, because that way I only store things that are true everywhere in the programs. I don't need to copy my state, and I don't need to join my state. It kind of sidesteps the problem, but especially as we had a paper last year where we showed we could compile a program to an SSA form as part of our analysis, and that compilation is very nice because in the SSA form you tend to create new terms whenever you learn more information about variables, especially at control flow joins, and that way you have a lot more flow insensitive relations because you have all these extra terms to handle. So for a very simple example, obviously it's when I built, if I have a term e and then I have e plus a constant or e times a constant, I can obviously build a relation. So for the join, which is what the SSA represents with these phi terms, if I have one branch where I have a linked to b via relation and another branch where I have a linked to b via the same relation, well, obviously these phi terms will also be linked via the same relation. And another interesting case is when I join constant pairs. So if I know I have a branch where x equals 2 and x equals 4 in the other branch, y equals 1 on one side and y equals 3 in the other branch, then I can actually find a relation between them. It's just finding a line between 2 points in 2D space. You can always do that. Of course, this is specific to the TVPE relation, but for other relations, you can usually find a value that matches an arbitrary constant pair. And these might seem cherry-picked examples, but they are sufficient to show the example I've shown in the beginning, or this one, which is essentially the same but simplified. It's when you have simultaneously increasing loop counters, because if you run a non-relational analysis on this guy, what you'll find is that you have a precise value for I, because you're going to identify that I is a loop counter, and so narrowing will be able to reduce it to a precise value, but you won't get a precise value for j. However, with labeled union find, on your first iteration through the loop, you'll know I is 0, j is 4 on the side. Well, before the first iteration. After the first iteration, I is 1, j is 3. That way, no, not 3, 7. That way you can deduce that j equals 3, I plus 4, and in subsequent iterations, that relation will be maintained. So at the end, you can get a precise value of j from the precise value of I. So yes, to conclude, I've presented the labeled union find data structure, which is an extension of union find, which adds labels to the parent edges, and with the requirement that labels must have a group structure. And then I've shown how you can use that data structure to represent a very efficient weakly relational domain, thanks to the very fast transitive closure computation. Of course, this is limited to injective relations that form a group, but as we've seen, it can combine with other domains to essentially shrink the space of variables the other domains have to consider. Now, this has been implemented both as part of the Codex Static Analysis Library, so an abstract interpretation library, and a Colibri2 constraint solver. So we already have two slightly different use cases, and you can check out the artifact or the paper if you want to learn more about the implementation. And finally, yeah, we have some postdoc positions, so if you're interested by our work, feel free to contact my supervisor.
Okay, questions?
Thank you. How do you compute abstract unions or widening or approximation of pairs of abstract states?
So the idea, yeah, is that we only store relations that are true everywhere, so we don't really need to widen. And part of that is handled by the SSA state, which will create new terms upon widening. And these new terms won't have the relation they used to have if we can't show that they hold on both of the values.
Okay, so you don't have any widening or abstract union?
We have a join. So yeah, as I mentioned, we mostly focused on the imperative version because it's faster, but we also have a functional version of union find, and we do have a join operator. It's a bit complex. It's detailed in the annex of the paper. But essentially, the key algorithm for the join is that we use Patricia trees to represent our union find pointers, and these Patricia trees allow us to get to the diff of two states in n log d time, d log n time, where d is the difference and n the total size. So you don't have to explore the whole state space. You can get the diff relatively faster.
And is it optimal in terms of precision, or is it approximate?
It is optimal in terms of precision. We've shown that we don't lose anything, yes.
Other questions? I had a question. I was just trying to understand. So is this as precise as octagons? Or what is the precision relationship?
No, it's not as precise as octagons because we store weaker relations. But yeah, the argument on my little speech at the beginning is that we're much faster than octagons because we don't have the cubic closure to compute.
So do you vision the practical application would be to store certain relationships maybe in a flow-insensitive manner using your new data structure, but then also retain octagons for things that you need to track flow sensitively or some other abstract domain?
Yeah, yes, like I mentioned, one of the interesting aspects is that the combination with other domains where you can shrink the space, and essentially you could have octagons between your different variable classes, but because you've grouped variables in classes, you have fewer variables, and therefore your octagon domain is faster.
Got it. Okay, another question.
Yeah. At least I know that the union find can be implemented in the consistent way or persistent way without using mutable features, using a rank optimization. So why didn't you use a rank optimization instead of the path compression?
You're talking about persistent arrays, that kind of data structure?
I'm sorry?
Are you talking about persistent arrays?
A persistent union find.
And these use persistent arrays inside. So actually, this is funny because if you asked the question 2 weeks ago, I'd have given you a different answer. I initially thought that would be very bad because persistent arrays, essentially you only have one copy at a time. So they're fine when you're just going down a branch and then going down the other branch, you just have to roll back. But when you want to do the join, you have to go back and forth between both of your branches, and that's actually quite expensive. But, so that was my initial reasoning for saying we can't use persistent arrays. What I've started to realize is that a key ingredient as to why the join isn't completely too expensive to compute is that we can find the diff quickly. And maybe we could use a variant of persistent arrays where instead of going back and forth to check the values of each state, you just do one pass, accumulate all the diff, and then use that to create your join. It's just an idea. I haven't tested it or implemented it in any way, but it might be worth checking out.
Okay, let's thank the speaker again. Let's thank all the speakers.